Hello, I'm Om, and in this video, I'm discussing the proposed design for the CPU architecture. These are the topics which we are going to be covering in this video, and this is a brief overview. So, coming on to the CPU architecture, this is the diagram of CPU that consists of several logic gates such as A register, ALU, D register, PC, and MUX. PC just means program counter and MUX means multiplexer. We already knew all these from our previous tasks, and these are just some basic logic gates which we are going to be using for implementing the CPU code. So first step of ours will be to deriving the API of CPU, which just means we have to specify the chip name, input and output pins, and function of CPU. For now, let's do not jump into the logic gates and focus on starting with an abstraction of this chip by having the logic gates in the diagram so we can identify input and output pins of the CPU. Now, this is input and output pins of the CPU. As we can clearly see that we have three inputs coming into the CPU from different sources in the computer. These inputs are instruction, enum, and reset. Now, instruction in now coming on to the next slide, we have computer system. In this, we are discussing the same input and output pins. So in this diagram that we use for hack computer, here we see the CPU is further connected to instruction memory and data memory. Here we see the CPU takes instruction from instruction memory and also takes value of selected D memory register as another input. The reset input tells us whether we bring CPU back to the initial state, that is, start of operations of CPU again. Now coming to the outputs that are connected to data memory and instruction memory as well. There are outputs WriteM, OutM, AddressM, and PC, which just means program counter. So coming back to the CPU architecture again, we see that ALU gives output which is returned to the data memory. To do this, ALU must specify things like content that CPU is going to write into the data memory, which is stored in OutM. Next, the address of write operation in data memory, which is the place where we put the content in the data memory. Finally, the output that allows CPU to write the content to the data memory. Now, I will be explaining the HDL code for the CPU that was provided in the task resources, and I will be doing so in parts to go into the details as much as possible. So here we have the header section specifying the CPU interface, consists of chip name and names of input and output pins. For CPU chip, the chip name will be CPU, obviously. Here in this code, input pins are 16-bit, enum, instruction 16, and reset. For output pins, we have 16 bits of outem, writeM, address M15, and PC15. This is the first part of this part section in CPU HDL code. Here we have three different gates, NOT and MUX16 gate. They allow CPU to function and performing specific operations. First, there are two types of instruction coming into CPU from instruction memory, which are A instruction and C instruction. So just for a second, let me give you a quick tour what are A instruction and C instruction. So A instruction has a symbolic syntax of add value, which can be number, that is a non-decimal negative value, or symbol if the value of A instruction is a number. Then the instruction will set the contents of A register to specify values in the instruction If it is a symbol, then the instruction will set the contents of the register to the value symbol points to, and this value will not be actual value in the memory register. Now coming to the scenes. Now, coming back to the HDL code, in the first line, NOT gate is used to tell us whether the instruction coming into the CPU from instruction memory is A instruction. But before that, the CPU decodes the 16-bit instruction into an opcode. The CPU decodes the 16-bit instruction into an opcode, and if 15-bit values of opcode is 0, then the instruction is an A instruction. Whereas if opcode is 1, the instruction is C instruction. If instruction is an A instruction, then the CPU takes the specified 15-bit value and stores the value in the A register. In the architecture, we know that the A register can be fed by either the instruction or the ALU output. Again, if it is C instruction, it performs the computation in the ALU, and ALU output is fed to A register. We use an AND gate to determine whether the instruction is C instruction, and mux16 is also used to select whether the instruction or the ALU output is stored into register A. Coming to the next part, we have an OR gate here. The load bit is A register will be 1 if either the A instruction or the ALU out is fed to A. Also, the A register stores the value that is fed there. It takes in the output A reg register in from the mux and output load A from the OR gate as it inputs and gives the output A out, which generates contents or the value currently stored in the register. We again use the mux16 gate, which takes output of A register and value selected in the data memory register is in M. This will select which one output A or M. Either A or M will be fed into the ALU depending on the 12-bit instruction value. And now we have the two OR gates, that is OR16. It means they are working on 16 bits obviously. These gates sets the ALU output in order to successfully write on the data memory. The first determines the address of write operations, and the second determines the content of data memory, and finally AND gate outputs the value. Now at the end, the PC contains address of the instruction to be fetched next. In these lines, the load bit of the PC are determined by the jump bits and ALU outputs. So basically they determine the jump condition and checks the ALU output to see if conditions are met. If instruction is C instruction and conditions are met, the PC is loaded with the value that will ask CPU to jump to specified location or symbol. If PC is not loaded, then it is incremented, that is, it will read the next instruction. With that, our HDL code will end and you can apply the code. Thank you. I hope it helped you a lot, and please provide any feedback.